Greetings to all members of the committee, professors, researchers, and participants. As we build smarter societies that rely heavily on AI to gauge public sentiment, ensuring the security and trustworthiness of these models is no longer just a technical luxury. It's actually a critical necessity. Transformer-based models have revolutionized our ability to decode human emotions from social media. Yet, the very source of their power, massive datasets, also exposes them to subtle and dangerous vulnerabilities, data poisoning. On behalf of our research team, Clarencia Agustin, myself, Devan Nicholas, and Vania Alicia Yoselin, alongside our advisors, Mr. Fikri Ramadan Tambunan and Mrs. Meliana from Binus University, Indonesia. I'm honored to present our paper for the 13th International Conference on ICT for Smart Society 2026, titled Evaluating the Robustness of Transformer-Based Models Against Data Poisoning Attacks in Social Media Sentiment Analysis. This presentation will be divided into 6 sections: Introduction, Literature Review, Methodology, Results and Discussions, Conclusions, and Recommendations. Transformer-based models like BERT and its successors have become the gold standard for sentiment analysis on social media. However, their continuous retraining on scraped data creates a critical vulnerability: data poisoning. In a data poisoning attack, an adversary injects a small number of manipulated samples into the training set, either to degrade the accuracy or to implant hidden misclassification behaviors. Because scraped social media data cannot always be audited, these attacks are practical and hard to detect. This leads us to 3 research questions. How does each poisoning strategy affect model performance? Does larger pre-training scale, Roberta, or domain-specific pre-training, like BERT confer robustness advantages over the standard BERT? And which strategy poses the greatest practical threat? To answer these, we selected 3 architectures. BERT serves as our 110 million parameter general domain baseline. Roberta adds optimized large-scale pre-training on 160 gigabytes of text, and BERT trained on 850 million English tweets, provided the closest distributional match to our Twitter dataset. Our work draws on 6 key studies. Devlins et al. BERT and Liu et al. Roberta set our architectural baselines. Nguyen et al. BERT established domain-specific pre-training for Twitter NLP. Steinhardt et al. Formalized the data poisoning threat model. Kurita et al. Demonstrated backdoor vulnerabilities in fine-tuned BERT, directly motivating our trigger injection design. And Wallace et al. Showed token-level triggers can cause consistent misclassification, forming the foundation for our backdoor evaluation. We tested 3 attack strategies. Label flipping directly inverts ground truth labels for a random subset, the most disruptive baseline. Trigger injection embeds a rare token into the training sample alongside a label flip, expecting the model to learn a hidden backdoor association. Clean label poisoning perturbs the text through synonym substitution and character level noise, without changing labels, bypassing any label auditing. What sets our study apart is that no prior work evaluates all 3 attack types simultaneously across 3 architectures on real social media attacks. That is the gap we address. We are using the Sentiment 140 dataset containing 1.6 million labeled tweets. We took a stratified sample of 200 to 300,000 tweets, split 70, 10, 20 for train, validation, and testing. Poisoning was applied to the training set only. Each model was fine-tuned under identical conditions. Learning rate of 2E of 5, batch size of 32, and across 3 epochs, at poisoning rates of 5, 10, 20, and 30%, repeated over 3 random seeds. This slide illustrates our overall research framework, which is divided into 3 phases. First, data preparation, where we filtered, pre-process, and split our dataset. Second, attack and fine-tuning, the core of our experiment. Here, we ran our clean baseline training, applied the 3 poisoning strategies at varying rates, and fine-tuned our BERT, Roberta, and BERT tweet models. Finally, the evaluation phase, where we tested the models on a health out test to compare against the baseline. To measure the impact of these attacks, we relied on 4 key metrics. Accuracy and macro F1 were used across all 3 attacks to evaluate global performance. Macro F1 is especially critical here to ensure both sentiment classes are treated equally, preventing misleadingly high accuracy scores. For trigger injection specifically, we evaluated the ASR, or attack success rate, to see how often the trigger successfully caused a misclassification. We paired this with clean accuracy, or CACC, to confirm the model still functioned normally on perturbed text, because a successful backdoor attack must remain stealthy and undetected. At clean baseline, Bertweet led an 87.99%, followed by Roberta's 85.98%, and Bert at 84.74%. Seed variance was below 0.2 percentage points across all models, confirming result stability. Label flipping was the only attack to produce a clear dose-dependent degradation curve. At alpha 0.05, the effect was negligible, but by alpha 0.3, BERT dropped nearly 4 percentage points down to 80.76%, with high seed variance indicating instability. Roberta lost around 2.78 points, and Bertid only lost 2.63%, maintaining the tightest variance throughout. Trigger injection produced an unexpected result. The ASR hovered at 45 to 50% across all models and poisoning rates, essentially random guessing for a binary task. The backdoor association was actually never learned. We attribute this to the tokenizer fragmenting the trigger token, the trigger being fixed at a single position providing too weak of a signal, and 3, fine-tuning epochs being insufficient to consolidate the backdoor. Clean label poisoning was similarly ineffective. Roberta showed the largest decline at only 0.63 percentage points in macro F1. Bertweet dropped 0.19 points, and Bert showed no net degradation at all. The perturbations simply did not cross decision boundaries. Synonym substitutions left enough contextual signals for fine-tuning to recover, and character-level noise was absorbed by the tokenizer. The following slides display the detailed graphs for our experiment results. Here, we have the poisoning evaluation dashboard, especially for the BERT model. Moving on, this slide shows the evaluation dashboard for the Roberta model. And finally, this slide presents the evaluation dashboard for the Bertweet model. Answering our RQ answers. For research question 1, only label flipping was a reliable threat. For research question 2, domain alignment outperformed scale. Bertweet's in-domain representations acts as a regularizer against label noise, outperforming Roberta's despite a smaller pre-training corpus. For research question 3, label flipping is the greatest practical threat. while trigger injection and clean label results reflect weak implementations, not transformer invulnerability. So, three principal findings. First, the performance ranking Bertwit over Roberta over Bert was reproduced reliably, confirming experimental validity. Second, label flipping was the only attack to produce reliable degradation, with Bertwit showing the highest level of robustness, consistent with domain alignment acting as a natural defense. Third, the null results for trigger injection and clean label poisoning reflect on conservative attack implementations, not architectural immunity. The key limitations are a single static trigger token, mod text perturbations, evaluation on one English-only dataset, and no defensive mechanisms tested. For future work, we recommend stronger backdoor methods like learned syntactic triggers, gradient-guided clean label attacks, expansion to multilingual benchmarks, and joint evaluation with defenses such as activation, clustering, and certified bounds. In summary, this study provides a comparative baseline for evaluating transformer robustness under data poisoning on real-world social media attacks. Our key takeaway is that domain alignment matters, and that stronger adversarial benchmarks are needed before any conclusions about architectural safety can be made. That's all from us. Thank you.